In the previous slide, we have talked about race condition when multiple processes wants to share the same data. In order to guarantee the correctness of manipulation of the shared data, so only one process can update the shared data at a time. To address this race condition problem, we formulate this problem as a critical section problem, showing in this slide. So for this critical section problem, it considers system of n processes, which is denoted as a P0 to Pn minus 1. So each process has its own critical section segment of code. So in this critical section, process may be changing the shared data, such as common variables, updating the shared table, or writing into the shared file, etc. So when one process is in its critical section to manipulate the shared data, so no other processes should be in their critical section simultaneously. So for example, we get two processes. We get a process A, we call it PA, and we get another process, we call it PB. And for PA, it has non-critical sections and also has instruction to enter the critical section. And then we have the critical section part. After that, we will exit or leave the critical section. And then maybe after that, we have another set of non-critical section. And similarly for process B, we may have some non-critical sections. And then we get an instruction to enter the critical section. And here is a critical section part. And leave, another instruction to leave the critical section. And after that, maybe we have some other non-critical sections. So the critical section for A and B may not be the same. So they may have the totally different instructions in the critical section. But the critical section of A and B wants to access the shared data and manipulate the shared data. So therefore, when process A is in its critical section, process B cannot be in its critical section. So similarly, when process B is in its critical section, process A can be in any non-critical section, and even at the instruction of enter critical section. If a process A is in enter critical section, it will stuck there until process B is out of its critical section. Then process A can get into its critical section. So the purpose of formulating the critical section problem is to design a protocol. So before getting into the critical section, each process must ask permission to enter the critical section in entry section. When the process finish the manipulation of a shared data, the process is ready to leave the critical section. Then the process will be in exit section, which means leave the critical section. Under the exit section, the process will inform other processes who wants to share the same data that the next process can access its critical section, then continually execute the remainder non-critical sections. The solution to address the critical section problem must satisfy three following requirements. The first one is mutual exclusion, which means only one process can be in its critical section among all the processes who wants to access the shared data. All other processes cannot be in their critical section at the same time. The second requirement is progress. So for this one, if currently no process is in its critical section, and there are numbers of processes wants to access their critical section. To make the decision that which process can be in its critical section may take a long time to decide it. However, the decision-making time could not be indefinitely, so it must be figured out within a limited time. The last requirement is bounded waiting. So when one process is requesting to get into its critical section, within the waiting time, the number of processes who can access their critical section before this process has to be bounded, which means if one process wants to get into its critical section, at most to wait bounded number of processes to finish their critical section accessing. Then this waiting process can access to its critical section. And also assume each process executes at a non-zero speed, which means as long as a process is making progress there, sooner or later the process can finish the progress. It cannot just suspend there and waiting forever without making any progress there. On the other hand, so no assumption on relative speed of n processes, which means that for these n processes, we cannot assume which one is faster and which one is slower. Their speed are totally random, so we cannot make any assumption about their speed. As long as the number of processes could be bounded for waiting, that should be enough. The critical section problem may not be only happen in user program. Actually, it may be happening in operating system as well. So for example, the data structure we have mentioned in the previous chapter, which is called task control block, which is used to store all the task information. It is maintained as a linked list. This data structure could be shared among different services, such as a scheduler that use it to decide which task can be put onto the CPU next, or the context switch that use it to decide what information should be switched out and which should be switched in. In operating system, how can we address the critical section problem? Basically, it is depending on the type of a kernel. So there are two approaches handled in operating system. One is a non-preemptive kernel. The other one is a preemptive kernel. For the non-preemptive kernel, so when a process is in the kernel, we just let this process do the execution until this process give up the CPU on its own, or this process gets out of the kernel, or this process just finish the execution. So otherwise, no processes will interrupt it. So therefore, for non-preemptive kernel, there's no race condition problem exists. But on the other hand, if the operating system belongs to preemptive kernel, so when a process is executed in the kernel, it can be interrupted by other processes. So under this situation, the race condition problem could be exist. So we need some mechanisms to address it. Unfortunately, nowadays, most of the current operating system, they belongs to preemptive kernel. So therefore, even within the operating system, we still need to consider the critical section problem.